we now have achieved our goal of understanding the motions of the sky, predicting which stars will be visible, which season, where on Earth, at what time of the night. There are some other things we'd like to understand. We talked about the orbital motion of the Earth and how it affects which stars are visible in the sky when. Of course, there's another phenomenon on Earth that repeats with a periodicity of once a year, namely the variation of the seasons. The climate on Earth changes once a year, and in fact the original interest in astronomy, much of it, was derived from the fact that by understanding or watching which stars were visible in the sky, say, early in the evening, you could predict the coming of harvest time or the time to sow or the inundation of the Nile or whatever, all other phenomena that were periodic with annual periodicity because they depended on the seasons. And the reason why the Earth's orbital motion is related to seasonal changes in temperature, of course, has to do with the fact that if you ever see one of these globes, it's always depicted in a tilted version. We all know that the globe is tilted by, I had it upside down, tilted by 23.5 degrees. But this is interesting, we're out in space. 23.5 degrees with respect to what? Well, it turns out that the globe is tilted by 23.5 degrees relative to the plane of the ecliptic, the plane in which the Earth orbits the Sun. In other words, if I want to imagine that the Earth orbits the Sun in a horizontal plane, then I must hold the globe tilted by 23.5 degrees rather than vertical, with the north celestial pole, therefore, off in that direction, 23.5 degrees away from the vertical. Contrariwise, if I want to present things with the north celestial pole vertical above me, then the plane in which the Earth orbits the Sun, and, of course, the plane in which the Sun appears to orbit the Earth, will be tilted by 23.5 degrees away from the horizontal, because it was horizontal in this frame of reference, and now I've tilted everything 23.5 degrees this way. So that the Sun's orbit around the Earth, or the Sun's motion along the celestial sphere, is not along the celestial equator, but along a circle tilted 23.5 degrees with respect to the celestial equator. This trajectory of the Sun moving to the east along the celestial sphere is called the ecliptic, and it's a circle tilted with respect to the celestial equator by 23.5 degrees. And if you take two circles and tilt one with respect to the other, they're hinged, so there are 2 points at which they continue to meet. Those are the points where the hinge meets, and so those 2 points are the points where the ecliptic meets the equator. Those are the positions along the Sun's motion when it is along the celestial equator, and the names of those points are the vernal and the autumnal equinox, for reasons we'll talk about in a minute, and these, it turns out, are the positions which, by convention, we chose to define the prime celestial meridian of 0 hours of right ascension. So when the Sun is at the vernal equinox, it is at 0 hours of right ascension. This means that the Sun is overhead at sidereal time 0. Sidereal time is off from solar time by 12 hours, and so the Sun is at the vernal equinox, if you look back at the last lesson, on March 21st, and it is at the autumnal equinox, 180 degrees away, 6 months later, at 12 hours of right ascension, on September 21st. So March 21st and September 21st are the days of the year at which the Sun is along the celestial equator and has celestial declination 0. And between those two, after the Sun passes the vernal equinox, it moves into the northern hemisphere of the celestial sphere, and its declination rises until at the full apex of its tilt, its declination is 23.5 degrees north, and then this happens on or around June 21st. Then it goes, on September 21st, it meets the equator, and on or around December 21st, the Sun is farthest south that it goes, its declination is 23.5 degrees south. And let's see how all of this relates to what we understand about the seasons. This demonstration will explain to us what the tilt of the Earth's axis, or equivalently of the Sun's motion around the celestial sphere, has to do with our seasons. So what we have here is, here's our celestial sphere view. The green line is the celestial equator. The tilted line is the ecliptic, the line in which the sun moves around the celestial sphere. And what we are seeing is that the sun is located now at the line of 0 hours of right ascension. In other words, it is the vernal equinox. This is the position of the sun on March 21st. Notice that on March 21st, the sun is at 0 hours at sidereal midnight, and so it's sidereal midnight when the sun is overhead. In other words, when it is noon, indeed, sidereal time is off from local time by about 12 hours at the vernal equinox. So this is the position on March 21st. The sun is on the equator. What this tells us, if we switch to an orbit view, is that the Earth's tilt at this point is such that the sun is neither north nor south. In other words, the tilt is perpendicular to the direction to the sun. And if we look from above, we see that as the Earth rotates about its axis, the line separating day from night, the sun side from the dark side of the Earth, goes right through the North Pole and equivalently through the South Pole. So over the course of a day, every point on Earth spends a half of its time on the sun side in daylight and a half of its rotation on the dark side at nighttime. Hence the word equinox. Night and day are equal length everywhere on Earth, and this happens whenever the sun hits the ecliptic. In other words, on March 21st, when the sun is at the vernal equinox, and again 6 months later on September 21st, when the sun is at the autumnal equinox. Now, what happens moving back to the celestial sphere, as time goes by, the sun moves around not the equator, but the ecliptic. So a few months later, the sun is now north of the celestial equator. Its declination at this point, its right ascension is 3 hours, so let's move it a little bit more. Its right ascension is 4 hours. That means that about 2 months have passed. It is now, if it was March 21st, it is now May 21st, and the sun's declination is 20 degrees north, which means the sun is well north of the celestial equator. That means that the sun is directly overhead at a point of terrestrial latitude 20 degrees. You see the direction from which the sun's rays are reaching Earth, and you see that the line separating dark from light on Earth no longer goes through the poles, but that in fact a whole region around the North Pole is encircled such that it is always in the sunlight. If we look from the sun, we will see that this whole region around the North Pole is always visible from the sun, and therefore as the Earth rotates, the sun never sets at the pole or points sufficiently close to the pole. And the sun impinges overhead at latitude 20 degrees, and as we move the sun farther along the ecliptic, it reaches its northernmost point in June, on June 21st, when the sun's declination is 23.5 degrees. The sun is now at the point where it's maximally north on the celestial sphere. What that means from the point of view of the orbit is that the Earth's north pole is tilted, the direction in which the Earth's north pole is tilted, which is always toward in the same direction, is now the direction of the sun. So now points all the way to within a circle of 23.5 degrees latitude around the North Pole are visible from the sun and therefore have continuous sunlight throughout 24 hours, whereas a full circle of radius 23.5 degrees around the South Pole is invisible to the sun, and the sun never rises there, and the sun is overhead at the tropic of Capricorn, the north of Cancer, the northern tropic, where the sun is overhead at a latitude of 23.5 degrees. And this means that this is the point at which sunlight impinges most directly. This will be the point at which solar heating is most intense on Earth. And as the Earth continues its orbit around the sun, or equivalently, as the sun continues its path around the celestial sphere, it again reaches an equinox on September 21st, at which point the line separating light from dark passes through both poles. The sun is overhead at the equator, and night and day are of equal length everywhere on the planet, and as the sun continues its path to its December solstice, in December, the sun is as far south of the celestial equator as it gets. It's at a declination of negative 23.5. At this point, the sun is overhead at a latitude of negative 23.5. The entire Antarctic Circle, latitudes within 23.5 of the south terrestrial pole, have 24 hours of sunlight, and latitudes to within 23.5 of the north terrestrial pole have 24 hours of dark. The sun never rises in the north and never sets in the south, and maximal heating is at southern temperate latitudes. And I hope that this picture, if you play with it a little bit, will clarify the relation between the orbit of the sun around the celestial sphere, the tilt of the Earth's axis relative to the sun. Note that the Earth's axis points in the same direction towards the celestial North Pole as the Earth rotates around the sun, and the changes in length of day and night and in terrestrial heating. So let's summarize this. Let's summarize what we've learned. Between March 21st and September 21st, the sun is north of the celestial equator, increasingly so until June, and then decreasingly so from June through September. And then from September through March, the sun is south of the equator, increasingly so until December, and then decreasing from December through March. When the sun is either, say, to the north of the equator, then days are longer in the northern hemisphere, and the sun is higher in the sky in the northern hemisphere because its declination is closer to the declination of your zenith if you're in the northern hemisphere. We saw that your zenith is located at a declination equal to your latitude. The sun will get closer to that zenith at its highest point if you're in the northern hemisphere when the sun is north of the celestial equator. And we saw that the sun's rays impact the Earth more directly in the northern hemisphere, so the climate is warming in the north and cooling in the southern hemisphere. And of course, the reverse is true from September to June when the sun is south of the equator. Inside the Arctic Circle, at least for some part of that time, the sun becomes circumpolar. The sun comes so far north that it's close enough to the celestial North Pole never to set for regions north of the Arctic Circle for at least one day. Of course, at the precise North Pole, the sun is circumpolar for 6 months. For precisely 6 months, so long as the sun is north of the celestial equator, the sun never sets at the North Pole, and the sun never rises at the South Pole, and then the inverse is true as when the sun is south of the celestial equator. And twice a year, at the equinox, March and September 21st, day and night are of equal length everywhere. The sun's declination over the course of the year ranges from 23.5 degrees south to 23.5 degrees north. What this means is that if you live at a latitude between 23.5 degrees south and 23.5 degrees north, between what we call the tropics, then as the sun's declination changes, there will be 2 days a year at which the sun's declination is precisely the same as your latitude. On those 2 days, the sun will be precisely overhead at your zenith at noon. Of course, if you live on the equator, those 2 days are the equinoxes, whereas if you live at the tropics, this only happens once a year at the appropriate solstice, June if you're at the northern tropic, December if you're at the southern tropic. Elsewhere on Earth, the sun will never be precisely overhead. Those are the regions, the tropics are the regions where at least once a year the sun is precisely overhead. Let's apply what we've learned to answer the question, how high the sun is at noon. And since we've started with Aristotle, let's continue with Aristotle. We'll be working at Athens' latitude of 37.7 approximately degrees north. Remember that noon is the time when the sun is highest in the sky. That's its meridian crossing. And so its altitude or its zenith angle will be determined precisely by the sun's declination. At the equinoxes, March or September 21st, the sun's declination is 0 degrees. Those are the days when the sun crosses the celestial equator, and for the course of a day we can imagine the sun fixed along the celestial sphere because it only moves by about 4 minutes along the celestial sphere. And if the sun is at declination 0, then at noon, its zenith angle is just the difference between its declination and the declination of our zenith, which is given by our latitude. Its zenith angle is 37.7 degrees, which means its altitude is 90 degrees minus 37.7, which is, I believe, 52.3 degrees. At the summer solstice, and the summer solstice is June 21st, so this is the northern summer solstice, the sun has reached a northern declination of 23.5 degrees north. The zenith angle, therefore, at noon, is the difference between our latitude and the sun's declination, which at this point is only 14.2 degrees. So, at noon, in midsummer, the sun in Athens will reach an altitude of 75.8 degrees in the sky. On the other hand, on December 21st, the sun's declination is now negative 23.5 degrees. So its zenith angle, when it's as high in the sky as it gets, at its meridian crossing, is the difference between plus 37.7 and negative 23.5, which is, if I got it right, 61.2 degrees, which means the sun's maximum altitude in the winter is only 28.8 degrees. You note that the solar heating in Athens is minimal in December 21st. December 21st is not by far the coldest day of the year in the Northern Hemisphere. The coldest day is usually somewhere around February. There's something like a thermal inertia. It takes time for the Earth to respond to the change in solar heating. There are many other complicated factors that govern climate, heat exchange between the equator and the poles and so on. But to a good approximation, solar heating is maximal at the summer solstice, and therefore in June, and about 2 months later in August, the temperature has reached maximum. By that time, solar heating is in decline, and with the same 2-month lag, the Earth starts cooling off. Solar heating is minimal in December, all this in the Northern Hemisphere. Of course, everything is reversed in the South, and 2 months later, the Earth is as cold as it's going to be.